So let's take a look at how to solve some problems involving waves. We'll start with the wave equation, which you should know now shows that the speed of a wave is equal to its frequency times its wavelength, which is this kind of strange symbol lambda. So here's an example of involving a wave that has a wavelength of 60 centimeters. So that's our wavelength lambda, and it propagates through a medium. Now, the word propagate might be unfamiliar to you. It's really just a fancy word for meaning that something moves through something else. So in physics, waves move through a medium or a material, and so this word propagate comes up quite a bit. The speed is given to us as 4.2 meters per second, so that's going to be our v. Then, of course, we are looking for the frequency. So the wave equation is going to be handy, but we got to make that conversion first because our speed is in meters per second and our lambda, our wavelength, is in centimeters. And so we'll need to divide by 100 to get this in meters. Now we're ready to use our formula. Might want to rearrange this so that the frequency is by itself. Notice, by the way, that frequency is a lowercase f as opposed to an uppercase F that we used before for force. It's a good idea to keep those straight and to use a lowercase v for the speed rather than that uppercase that we used for voltage recently. Putting in our numbers, the 4.2 would be divided by 0.6 to find our frequency. Now the units are a little unusual. When the meters cancels out, we're left with just 1/seconds. But that's not the way that frequencies are typically labeled, and we don't do it this way either. What we do is introduce a new unit called the hertz, and a hertz is defined as 1/seconds. And so this is what you see in problems and as the result of problems. You may have heard of hertz before if you know anything about computers and the speeds at which they manipulate data and so forth. Typically be in gigahertz or even terahertz. Definitely something that's common in our everyday world. Now, we're going to look at three different specific types of waves within our examples. One is a mechanical wave. Mechanical waves are waves where material itself is actually being moved by the wave. Not moved with the wave, but moved by the wave. We'll talk about that more as we go. In class, we would model this sort of wave using a large slinky. We could send pulses down that slinky, or we could make continuous waves where there are bumps called crests and troughs on both sides of the slinky. All right, so these mechanical waves are going to show up in this first problem. Two students are on either side of a long spring, and we're going to start with a pulse like we just showed in the video. A pulse is made, so just like a single little bump, and it takes 1.2 seconds for that pulse to move along the wave. Now, there doesn't seem to be any mention of frequencies or wavelengths, and that's because another way to think about the speed of a wave is the way we've been thinking about it the entire year, and that is to think about distances and times, which is what we've been given here. So if we know the distance that something travels and the time that it takes to do that, we should be able to find the speed using distance over time. We've done this before, meters over seconds. This ends up being 6.25 meters per second. So you can think about the speed of a wave just like you can think about the speed of a ball or a car or anything else, in that the wave travels through a certain distance in a certain amount of time. But you can also think again about the wave in terms of the properties of the wave, the frequency and the wavelength of the wave. So now we can do a part B of this question. On the same spring, if the student now moves her hand continuously, like we saw in the second part of that little video, we can determine what the wavelength of the waves should be. Because it's the same spring, then the wave speed stays the same. So the fact that we found this 6.25 meters per second, we can use this value in the second part. We're going to want to use the wave equation, v equals f times lambda, but we need to figure out what the frequency is from this given information. Frequency is just how often something occurs. So we have that info here, 6 cycles every 4 seconds. It's just not written the way it normally is. Frequency is going to be the number of events that happens per time. So for instance, if you eat 3 meals throughout a day, you could say that your frequency of eating is 3 meals per day. Okay, if you pick up your phone 50 times during a day, you could say that your frequency is 50 per day. So it's a number divided by a time. But in our case, we do want it to be per seconds. So we'll use this 6 cycles on the top and the 4 seconds on the bottom. And calculating 6 divided by 4, we get 1.5. Again, that's 1.5 cycles per second, but we use the unit hertz to represent that per second unit. All right, so our goal was to find the wavelength. We now have the frequency, and from earlier we have the speed, so we should be able to use the wave equation. Again, we can rearrange to get the lambda by itself, and that would tell us to take 6.25 divided by 1.5. Again, taking a look at the units just to make sure that they all work out. Remember that hertz is really a 1 over seconds, and so the 1 over seconds would cancel from the top and the bottom when we're dividing. And we do get meters like we would want to for the length of something. Let's take a closer look now at another type of wave called the sound wave. A sound wave is actually not a mechanical wave. It has to do with pressure moving through a material. But the speed of the wave still does depend on the material itself. The sound wave, or a sound wave, can go very fast. Like in a solid such as steel or wood, sound can travel tens of thousands of meters per second, an unbelievably fast transmission. In water, sound waves are typically in the thousands of meters per second, but in air, it's about 350, somewhere around there, 350 meters per second, which, to give you some perspective, if you imagine a football field, that's about 100 meters. So line up 3 football fields end to end, and that's roughly how far sound can travel in just a second. So still pretty fast. But sound waves do depend on particles for their motion. And so the faster the particles of air themselves are moving around, the faster the information can get transferred. And so temperature of the air ends up meaning a lot. We can calculate the speed of sound based on the temperature of air using this formula. So 331 meters per second is the speed if we're right at the freezing point of water, right at 0 degrees Celsius or 32 degrees Fahrenheit. And then as the temperature goes up, the speed also goes up. And it turns out through experimentation, it's been found that it's about 0.6 times the temperature to find this additional speed that's gained added on to the 331. Let's try this out in a problem. So imagine that you're watching a race and there's someone with a starter's pistol who's 120 meters away from you. So whether you think about it or not, there's going to be time. There's going to be a delay between when the pistol is fired and when you actually hear it. And that delay, that time for the sound to travel, will be different based on the temperature of the air. So let's take a look at the difference in time when it's a 4-degree day, which is about 40 degrees Fahrenheit, and a 38-degree day, which is about 100 degrees Fahrenheit. We'll first look at the speed of sound at each of those temperatures. So plugging 4 into this formula for the temperature, we get 333.4. Whereas if we plug in 38, we get 353.8. A difference of about 20 meters per second when you go from a cold day to a hot day in terms of the speed of sound. Let's see if that really affects, though, what we hear from that pistol shot. We're going to need to look at the difference in the times. So we'll calculate the times for each of these speeds individually, and then we'll subtract to find the difference. Let's use the old formula for speed, distance over time, since this problem is not dealing with frequencies or wavelengths. It's dealing with distances and times. Rearranging, time would be distance divided by the speed. So for this lower speed, the colder temperature, we would divide 120 by 333.4. The units do cancel out, and we do get seconds because we have 1 over seconds in the denominator. So 1 divided by 1 over seconds would give us seconds. But 120 divided by that 333 would give us 0.36 seconds. If instead we use the faster speed, we're going to get a smaller time. That turns out to be 0.34 seconds. So the difference can be found by subtracting those two numbers, and we see that it's really very small, 0.02 seconds. So you certainly aren't going to notice the difference, but in other situations, that difference between the speed of sound by temperature really does cause a change into how things are heard. Now, another area where we can think about sound waves is how they are able to bounce off of surfaces. So why do we care about this, or why is this important suddenly with sound waves? Well, sound waves travel so fast that there's really no way of them moving without encountering some sort of an object. So this idea of sound waves reflecting or bouncing off of materials, it just happens all the time. One area or one example of where we might hear this is with an echo. So when you hear an echo, you are hearing the sound wave that you made bounce off of something and then come back again. So the sound wave actually has to travel there and back, and that's an important part of solving the types of questions we're going to look at here. So imagine that you're on some sort of an adventure and your friend Jeremy lets out a holler, and there's this vertical cliff nearby, and so his sound that he's made, his voice, will reflect off of that cliff and then come back again. And so we measure that it takes 1.9 seconds for the echo to return. And from this and the temperature in the air, we can determine the distance to the cliff. Now let's go back and think a little bit more about that 1.9 seconds. That is the time to go there and back. That is the time for the sound to travel there and back. But the distance we're going to be looking for is just the distance there. So we need to keep that in mind as we're thinking through these sorts of questions. Let's go ahead though and figure out how far the sound can travel if it's traveling for 1.9 seconds. We'll need to know the speed of sound. So we need to know the temperature of 10 degrees. 0.6 times 10 added to 331 gives us 337 meters per second. We are looking for distance, so we will rearrange the equation distance equals velocity times time, or speed times time. And so we find that the sound actually traveled 640 meters during that 1.9 seconds. But again, that is the distance to go there and back. That's the echo that you're measuring. And so the distance to the cliff would only be 1/2 of that distance. So that's going to be 320 meters. So we've seen that with different types of waves, sometimes we're going to be using just this old formula, v equals distance over time. Sometimes we're going to be using the formula frequency times wavelength. You just need to look at the type of wave, type of information that you're given. One last thing to mention is that these ideas do also apply to the speed of light. So we will talk more about light and its nature later on, but light has a very consistent speed within most applications of our life. So the speed of light does not change based on temperature. It travels at the same speed within air. In fact, it basically travels that same speed even if you're in a vacuum like space. What changes the speed of light is it has to be something a little bit more drastic, like when light travels through glass or when it travels through water, then there is a change to the speed of light. But for purposes right now, we're just going to stick to examples where we're working with light traveling through the air. And in that case, there is a particular value for the speed of light, and it represents the fastest speed that anything can travel. So it's given a special symbol, c. You may have seen this in famous formulas like E equals mc squared. The speed of light is crazy fast. 3 times 10 to the 8th meters per second. That's 300 million meters per second. The formulas are the same as what we've been talking about, so I'm not going to show another example here. You just need to kind of slow down a little bit, make sure that you get your scientific notation straightened out.